Okay, perfect. So, hi everyone. Thanks for coming to my talk here. So today I am gonna talk about our next generation radio processing pipeline that we are planning to introduce at the Allen Telescope Array, and how we use this next generation pipeline to process our FRBNN, that is our fast radio burst neural network detection pipeline that runs inference in real time, leveraging the TensorRT using the Holoscan pipeline. So I'm sure most of you are familiar with the Allen Telescope Array, but in short, this is in Northern California. It's a radio interferometer with 42 elements. Each element is around 6.1 meter in diameter, and currently we have 28 of them working with the new upgraded dish. Each antenna will get 1.5 gigahertz of bandwidth, and in total we have 3.3 gigahertz because we have two polarizations. So the entire telescope can produce around 84 gigahertz, and that equates to around 2.4 terabits per second of bandwidth. We use the RF sock boards, that is AMD ADC, to collect the samples, and those RF sock boards will send the data to our compute backend. It will perform some coarse channelization with polyphase filter bank, and then send over 100 gig link to our compute nodes. So what we used to do is to use HPGAPI, that is a CPU-based pipeline, to get the samples arriving at the computer and processing it on the GPU, uploading to the GPU, and then downloading back to the host, and do something else like write a file. And that was all handled by a CPU-based HPGAPI. And we thought that can be improved. And the way we improve this is to make it sure the samples never get access to the CPU. So sample get received by the machine and gets uploaded back to the GPU instead of going to the CPU. And this is exactly what the Holoscan pipeline helped us to do. I have a talk at the GTC 2024 that you can search for this RVLM, this title here, and you can learn more. But in summary, that's a technology where you can get the acquisition of the signal, so you can receive the packets and sort them out into a contiguous memory. Then you need to process it. That can be handled by Blade. That is our previous DSP pipeline. So beamforming, correlation, channelization perform the processing. It's an umbrella term. And then after everything's processed, everything's reduced, all your 28 antennas are reduced back to just a single beam. You need to start it somewhere. So you need to also handle the storage. And for this, we are using like our GPU direct storage that also copies the memory from the GPU directly to the NVMe without the CPU involvement. So you can see here, instead of connect-X connecting to the CPU and then the CPU connecting to the GPU, you have a straight path from the connect-X, that's the NIC, straight to the GPU, and the CPU is just acting like a memory management. One thing that we envisioned is with the Holoscan pipeline, the new generation pipeline, is to run the beamforming and also the correlator at the same time, and choose what else we can do with that data. For example, if we want to run an inference, if we have a machine learning model, such as the FRBNN, we can get the data from the beamformer and then run the inference in real time. The output of the beamformer is passed to the TensorRT Holoscan module, that is the inference is run, and you get a result. You can save that data back if you also implement a GPU direct NVMe raw voltage playback cache. So if you detect something interesting, you can tell this cache, say, hey, that was interesting. Can you save that data on disk so we can analyze later? And a real-time inference allows you to do this kind of situation. So what we achieve here is a tiered system. So we have Nexus, that is the orchestrator. It will assign the compute clusters, because you cannot process 2.4 terabits of data into a single GPU. You need to get everything into multiple computers. So Nexus will launch the installing instances and make sure everyone is running at the same coherently. So every single instance is processing each buffer at the same time. So, and also some metadata. Every single node needs to know where the computer, where the telescope is pointing for correlation metadata that is also written on the file. So Nexus will broke that between the nodes. Then we have Stellene, that is a development kit that extends the functionality of Holoscan. And Holoscan is inside Stellene. So Stellene calls Holoscan and also implements some extra modules, such as CyberIFR for visualization. That is a real-time visualization tool that we use to see the pipeline, the spectrogram being plotted at the same time. Or in the case of the FRBNM, we can hook up the input and output. And whenever something gets detected, the plot can be highlighted. For example, Blade, that is our internal framework to do beamformer correlation channelization. TensorRT, that we use for the FRBNM detection library, that is provided by the Holoscan pipeline. And also a mesh network operator that is also provided by Holoscan, that will take the UDP buffers. We'll get the first 12 bytes of each packet that contains the metadata, send that to the CPU, and then get the actual data, that's the samples, and send to GPU memory. So the CPU never receives a piece of data, it's just metadata, and it manages from there. And ultimately we have the GPU direct buffer that basically uses GPU direct storage, that is a NVIDIA technology, to write data to the disk automatically without going to the CPU. And Stellene provides all of those, working with Holoscan for the radio telescope. So if you want to deploy that on your shiny new telescope, you can get Stellene and adapt your telescope to use it instead of rewriting everything that we spoke here. So that's an example of visualization that we can get using the CyberIFR in conjunction with Stellene. So we can see the waterfall and also the the line plot of the spectrogram. And also can do other fancy stuff. We can access that from the computer using WebRTC. So instead of sending all the data from your computer from your server to your computer, you can basically encode the video on the server and just send the video instead of sending the data. So that will save you, in the case of the ATA, 100 gigabits per second. You just send a 5 megabits video to the client, and you can see with high fidelity what the telescope is seeing. Again, Stellene, it encompasses all the Blade TensorRT transport file system, so you can write HDF5 files directly from that pipeline. and access that is the matrix metadata in instancing, working with the telescope abstraction layer. So instead, when you're putting that on your telescope, you don't need to rewrite the internals of Nexus. You just need to rewrite the telescope abstraction layer that will break the frequency, for example, which frequency the telescope is tuned to. Instead of rewriting that on Nexus, you put that in the abstraction layer that communicates with your existing telecommunication stack of your telescope and translates that to a language that Nexus can understand. So simplifies the integration with your telescope. You don't even need to change any data of your telescope. And we tested the new pipeline with the Allen Telescope Array. We pointed towards Mars, and we detected Mars Odyssey phase modulation carrier here at X-band that was recorded with Stellene and visualized with MPIFR. We can also see Tianwen, that is a Mars orbiter, same thing, same signal. We also pointed to the geostationary belt and got the GO-16, that is a weather satellite that takes pictures from Earth, the weather from Earth, multispectral weather, and beams out to Earth. That's a signal that we could decode. So those photos on the top right corner are GO-16 photos. And also, the farthest object that we could decode is this Stereo A, that is a geostationary heliocentric, or using heliocentric orbits, so it's orbiting around the sun, taking photos of our sun and sending back to Earth. That's for space weather and like predicting conditions that might be harmful to Earth. It has a camera pointed towards the sun, and it transmits these photos every now and then. So we also were able to decode that. And I know this is an FRB conference, so let's go to the model that we used to detect the Crab Nebula. So as you know, the Crab Nebula has a pulsar in the center, and that pulsar emits giant bursts every now and then. And we were able to detect using the inference without any other traditional help, just feeding the spectrogram directly from the pipeline after the beamforming to the FRBNN that it was running on the TensorRT inference block from Stellene and Holoscan. And that flagged that the time samples into is saying there is a 99% chance this is a pulsar, and after analyzing it, the dispersion was correct, and we were satisfied that was a true detection. So going further on the architecture of the model, so it's a very, very lightweight model. So that means it's 82 megabytes, the entire model, instead of like the hundreds of gigabytes that are today's LLMs. This one is 82 megabytes. It's probably smaller than the slides of this presentation. So it's very fast and very well optimized, and it can run in real time using the TensorRT. So everything is integer 8, so everything is very, very optimized and can process like gigabits per second of telescope data. This model was trained using ATA background data, so like recordings with no signals. We started with that. So there's a diagram here. We started with that background noise, and then we added some training, so more than 300,000 trainings, signals. So background noise, then we added like a burst, a dispersed burst, and then saved that in a data set, made sure everything was balanced correctly, and then we trained that model and came up with the 82 megabyte final weights, where we can where it has 99.1% accuracy. So it's fairly accurate and very small. The publication will be in Astronomy and Astrophysics by the end of the year, and make sure to follow that if you want more information. So, and going for more of a pipeline side of what we tried is the whole scan transport gets the samples in. It's being formed by blade. Then we run some detection that is basically a Stokes side. And then we integrate and stack that information. So we don't need all the time resolution. So we integrate them into something more manageable. And then we run the inference using the TensorRT module. And we process 4 seconds of data in 60 milliseconds. So that means that we can increase the size of the model and also or run more models at the same time. And this is what we want to achieve. And of course, we had all the partnership with NVIDIA that we had like press releases. Bob Pete spoke about our partnership. And yeah, so this is what I mentioned with visualizations and stuff. That every time we see a burst, we can see a green fan. In the future, we want to increase the 1.5 gigahertz into 16 gigahertz. So that's an order of magnitude more data to be processed by the ATA. So we need more computers. We are testing the NVIDIA IGX RN for inference, and also a super microcomputer with 4 RTXs Pro 6000 Max-Q that has 384 of VRAM that will give us more headroom to do more like LLMs or even like larger models. So that's the next generation, and that's my presentation, and I would be happy to answer questions now.
Thank you. I think any questions? So, looks Jayanta. Jayanta, please.
Hi, Luigi. It's a nice talk. I have a question about this gravity server which you are talking about. So the holoscan, what I understand, like you have a correlator and beamformer running as a one block in the blade, right? And then output of the beamformer is as a time frequency, which directly go for the AI inference. Is that the way to understand it?
Yeah, so we have here the pipeline. So basically we chose to run the beamformer, but we can also do a correlation run if you want to. Mm-hmm. Instead of beamformer, and the only difference would be that wouldn't have like detection and integration, because after correlation you do the imaging, so you can modify the inference block to run like imaging instead of IQ waterfall. That would be 100% possible, and everything would be running inside this server that runs on the GPU. The data would never leave the GPU inside the server.
Yeah, just one short thing. Like in one of the slides, I saw that your GPU direct thing. You said that when the event is directed, you have a direct GPU direct to disk, which is like around 50 gigabyte per second. So yes. I was wondering, is directly from GPU to disk?
Yes, it is. So we have Selene provides a file system block that can use GPU direct storage to copy the data from buffer on the GPU directly to the file on the NVMe, and that can be either a binary file or a HTF5 file. So with all the metadata pre-filled by the CPU, the GPU is just instructed to copy the data it has into that memory address on the NVMe. So we are very flexible on which files we can generate with that block.
Thank you. And I'm just wanting to ask one question related to the web-based tools and the way earlier generations of our city search have been done, and what kind of user interface it provides. Does it give access to?
Yeah. Sure. So Nexus is a web interface. So we were thinking about what's the best way to make that available to the astronomer, and everyone's familiar with web. So it's a very familiar web interface that you can schedule observations. You can set what the observation will do in a flow graph. In a flow graph level, so you can like block input, then you can like do beamforming, and then you can save the file, for example, just like a simple example, and you can configure that using a flow graph interface on the web. So you just navigate to you join the VPN of the telescope, you go to the web page, and the control is there for you.
Thank you, Luigi. I think people may later offline interact with you, and we are going to move on to the next session. Thanks once again.
Yeah, no problem. Yeah, my email is available if you guys want to send me an email. I'm happy to answer your questions there. Thank you very much.
Thank you.